Hi students, in this lecture we are going to learn organ pipes. You can see in our practical life flute, clarinet, saxophone. Like these musical instruments are cylindrical in shape, which are known as organ pipes. Let us see how they are working, how to find their frequencies. See explanation part here. Right. So we are taking here a simple diagram. We are taking a one cylinder. So one end is closed and one is open end. This is known as a closed pipe. This is known as closed pipe. This is known as a closed pipe. Suppose length equal to L. See, if you produce a sound here, sound travels inside, reflects from this closed end and comes back. The one which is reflecting and the one which is going inside, now they superimpose. I am repeating. The one which is going inside and one is reflecting, now they superimpose, right? Then they form standing waves. So this is an example for interference in space. The relation is that here path difference is not depending on time, it depends only on position. See how we are writing that. Let us take two traveling waves. We are taking here sound waves. P1 equal to P naught, or we can say delta P1. This is delta P naught because we're focusing changes. Change in pressure equal to maximum change delta P naught sine. It is omega t minus kx. Next, delta P2 that is equal to delta P naught sine omega t plus kx. Right. So one is traveling along positive x, other is traveling along negative x. That means we are taking here x-axis is now like this. And this is x-axis. So one is now traveling means one comes after reflection and one is instant one. So how we take this as sound wave means one way is like take here one tuning fork. Take one tuning fork. When prongs are vibrating like this, they vibrate like this. When they vibrate, they push the air particles here into the pipe. I am repeating. When the prongs of the tuning fork are vibrating, these are pushing now these air molecules into the pipe. Means here compression and rarefaction, vibrating like this. So sound goes inside, reflects and comes back. So now they superimpose. Now see what we get here. Resultant delta P equal to delta P1 plus delta P2 that is equal to 2 delta P naught sine A plus sine B, 2 sine A plus B by 2. That means sine omega t. Check once. Sine A plus B by 2. That means kx gets cancelled. cos A minus B. That becomes now cos kx. Okay. And this is written as 2 delta P naught cos kx into sin omega t. If you observe carefully, in the place of delta P naught, this is now 2 delta P naught cos kx. So in the place of pressure amplitude, we are having 2 delta P naught cos kx. That means pressure amplitude is depending on the position. If you remember standing waves in strings, there what we have discussed exactly same thing, right? There we got like 2a cos kx sin omega t. Different points having different amplitudes, but all having same frequency. So now this also exactly same. Different points having different prior amplitudes, right? For example, for example, if you consider this open end, if you consider this open end as origin, means x equal to 0. Okay, means if I am taking left as a positive x, okay, left as positive x, this x equal to 0 is now left as means this open end as x equal to 0. Just a minute here, it is right. We are taking along the pipe as a positive x axis and taking the open end as x equal to 0. In this case, see what happens here, x equal to 0. This becomes now maximum change in the pressure, right? It is maximum change, but that means this is not matching here, right? Why it is not matching? See carefully. According to the equation, we have to take origin is now. Origin is the closed end. Taking the closed end as origin and this as cos to x axis. So why we are changing? See carefully. At the open end, pressure equal to pressure of atmosphere, and that is a constant. I am repeating. Sound traveling inside and reflects. Right now, those two are superimposing to form standing waves. These are now longitudinal standing waves. Earlier, we have discussed in strings stationary waves. Those are transverse standing waves. Now, these are longitudinal standing waves. And at the open end, pressure equal to pressure of atmosphere, which is a constant. That means at the open end, pressure does not change. I'm repeating. At the open end, pressure does not change. That means this is a pressure node. What is it? It is a pressure node. I'm writing here open end. Open end. Open end is pressure node. Why pressure node means their pressure is not changing. That is also known as displacement antinode. Displacement antinode. Okay. So we got first point open end. It is a pressure node. Why means that is the pressure of atmosphere which is a constant. That is also known as displacement antinode. Coming to closed end, their change in pressure is maximum because the particles are compressed, right? So coming to closed end, closed end is corresponding to pressure antinode, pressure antinode, or it is displacement node. Okay, right. Now see carefully. 2 delta P naught cos kx means when x value is 0, this is maximum. Means change in pressure is maximum, right? Therefore, if you are taking here pressure antinode, that is closed end. So if you take closed end as x equal to 0, then this is the equation. Okay. Suppose if I am taking x equal to 0 is now open end, then we have to write in the place of cos, it is a sine kx, because here it is a pressure node, means there is no change in the pressure. Okay. So coming to here, should we write sine kx or cos kx? If you are taking the closed end as x equal to 0, it must be cos kx. If you take open end as x equal to 0, that must be sin kx. Okay, right. So this is now equation for standing wave, right? Now let us see a few points regarding this. If you remember in strings, reflection from fixed end, reflection from fixed end, shape inverted, right? In case of a string, reflection from free end, a ring was here, going like this, while coming also no change of shape, means there is no inversion. Okay, this is what we have learned, right? In strings, reflection of a pulse from a fixed end, that is inverted, there is a phase change of pi. When reflection takes place from free end, then there is no inversion, it simply comes back as it is. Now coming to here, if a sound is now reflecting from open end, see these points very carefully. If a sound reflects from open end is pressure node. What is it? Open end is pressure node. Compare now this, compare that with this reflection of the pulse from fixed end. Get the point? That means if a compression is now falling on the open end, a compression comes back as rarefaction. I am repeating, a compression from open end reflects as rarefaction. If rarefaction comes here, that reflects as a compression. Means there is a phase change of pi. This is what we can say comparison. A pulse reflected from fixed end, there is a phase change of pi, means the shape is inverted. Exactly same logic. When sound reflects from the open end, if compression falls, compression reflects as rarefaction, rarefaction reflects as a compression. There is a phase change of pi. If sound reflects from, if sound reflects from closed end is now pressure antinode. It is just like reflection from free end. I am repeating, reflection from free end. In this case, what happens is no phase change. That means if a sound reflects from closed end, suppose a compression pulse, it reflects as compression pulse only. If rarefaction, it comes back as rarefaction. That means there is no phase change. So when sound reflects from closed end, no phase change. When sound reflects from open end, there is a phase change of pi. So these points we have to keep in mind. Okay, right. Let us see notes for these points. Yeah, right. These are now standing waves, or you can say longitudinal standing waves. This is example for interference in space. Why means there it is depending only on x. We got cos kx, right? When x is changing, then amplitude is changing. So it is not depending on time. That's why this is called interference in space. Okay, right. So first one sin omega t minus kx. Next omega t plus kx. Then it is a 2 p naught sin kx cos omega t. Right. Next, open end is a pressure node. What is it? Open end is a pressure node or displacement antinode. This we have discussed that open end is a pressure node or displacement antinode. Closed end is a pressure antinode or displacement node, right? Because their particles cannot vibrate at a closed end. That's why displacement node. Next. So we are having one point here, end correction. Here, there we discussed like open end is a pressure node, but actually pressure node is not exactly at the open end. It is slightly beyond the open end. Okay, it is slightly beyond the open end. So its distance from the open end is called end correction. Its distance from the open end is called end correction. Okay, and that value is given by 0.3 times diameter of the pipe. This is 0.3 times diameter of the pipe. So what the end correction means? Pressure node is not exactly at the open end. It is slightly outside the open end. So from the open end to pressure node, that gap is called end correction. And that value is given by 0.3 times diameter of the pipe. Okay, right. Then see next point which we have discussed. If a compression pulse is incident on the closed end means it is a pressure antinode, right? It reflects back along the tube as a compression. So compression comes as compression. Okay, that means a longitudinal pressure wave is reflected from a closed end with no phase change. So this is what we have discussed, right? Next. And when it reflects by an open end, there is a phase change of pi. That means compression pulse reflects as rarefaction pulse and vice versa. That means rarefaction reflects as compression, right? So these are the points we have discussed till now. Now we have to focus on frequencies. Okay. See how we take frequencies. Let us take. So we have discussed now closed pipe, length equal to L. We are saying that in first harmonic, it is same as a strings, okay? Standing waves and strings. This is a pressure antinode and this is pressure node. If you take a first harmonic, antinode and node, antinode and node, diagram must be like this. It's not exactly correct. It comes okay like this. That is now pressure node. Okay, this is the pressure antinode. And node to antinode gap equal to lambda by 4, right? But we are saying that this is a slightly outside, right? Slightly outside. That means let us make a diagram once again. Right. Pressure node slightly outside. So this is antinode. We have to join like this. Shape comes like this. Okay, na? Shape like this. Right. This is now tube length. From here to here, the separation is end correction. Okay. That means we are knowing that node to antinode separation equal to lambda by 4. Lambda by 4 equal to L plus C. Okay. Then lambda equal to 4 times of this length. Okay. Next, this is now known as a first harmonic, right? Pressure antinode, pressure node. See, next possibility, next possibility. So having here one half loop, and this is now one complete loop. So lambda by 4 separation plus lambda by 2. 3 lambda by 4. 3 lambda by 4 is equal to L plus C. Right? This is third harmonic or first overtone. Okay. If you generalize, if you generalize, we can write lambda as lambda equal to 4 into L plus E, 4 into L plus C. In the place of 3, I am writing it is a 2n plus 1. N corresponds to overtone. N corresponds to overtone. So n equal to 1, this becomes 3, third harmonic. Okay, right. Now frequency. Frequency is given by F equal to V by lambda, where V is the speed of a sound in that medium. V by lambda. Then see what we get. V by lambda means it is a 2n plus 1, 2n plus 1 into V by 4 into L plus E. Okay. That is now frequency for closed pipe, where N stands for overtone. So first overtone means N equal to 1. That is known as third harmonic. N equal to 2, second overtone. That is a fifth harmonic. This is the same as in strings. In strings, we have discussed one end fixed, other end is free. So same formulas, right? And most of the cases, we neglect end correction. Whenever you are given diameter of the pipe, then we have to consider end correction. Okay. So most of the cases we are neglecting that value. So it depends on the given problem. So this is about closed pipe. And for closed pipe example is, it is a clarinet. I will show diagram here. So this is now closed pipe. For nth overtone, we got how much? 4L by 2n plus 1. Then for nth overtone frequency, 2n plus 1 into V by 4n. So this is when end correction is not taken. If you are taking end correction, I think here we have taken wrong. This is not n, this is 2n plus 1. Actually, this I have written formula wrong here. This is actually 2n plus 1 by V into 4 into L plus C. Okay. So this you have to correct here. And in this, only odd harmonics are possible. In this, only odd harmonics are possible. Okay. So here you have to change the formula. This is this same formula 2n plus 1 into v by 4. In the place of L, write L plus C. Okay, no? So I have written here wrong. That we can change. And this is a clarinete. You might have seen this in many marriage functions, right? So this is open end. And this end is closed. That's why this is example for closed pipe. This is what we call clarinet, right? Let us see now open pipe. So coming to open pipe, almost same as closed pipe, only change. It is open at both ends. So it is open at both ends. That means open ends are now pressure nodes. Diagram becomes this is a one complete loop, right? Node, node. Midpoint is now antinode. So this is looking just like a string fixed at both ends, right? First harmonic, single loop, right? So n equal to 1, first harmonic. And in this, what I can say is, see carefully, n equal to 1. Lambda by 2 is equal to L plus 2E. Why we have taken 2E means this node slightly outside. This node also slightly outside. So adding here E and adding here E, here also E. Total is now 2E. So L plus 2E, that is now lambda by 2. From this we get the value of lambda. If you take next harmonic, then we are going to get two complete loops, same as a string, fixed at both ends. That means, right, diagram we have to make it properly. It is like this, okay? Having two loops. Second harmonic, lambda. 2 into lambda by 2 is equal to L plus 2E. If you take nth harmonic, it becomes n into lambda by 2 is equal to L plus 2E. Therefore, frequency for nth harmonic is V by lambda F value V. But we are knowing V value. Coming to lambda, it is now see how much we got. It is N V by 2 into L plus 2E. This is the frequency of nth harmonic. What is it? Frequency of nth harmonic. Okay, right. Cross check once here. Lambda. Lambda is 2 into L plus C by N, right? And for this example is flute. Example is flute, open pipe. We can see notes for this. Yeah. So for nth harmonic, wavelength is 2L by N, right? This is when end correction is not taken. Okay. Then for nth harmonic, it is N into V by 2N. So these two are taken without end correction. If end correction is taken, then F equal to N V by 2 into L plus 2E. Okay. And this is a flute. You are knowing that. So this is example for open pipe. Okay.